So this is work together with an undergraduate student, Jordan Götze. The motivation for this work is the wish to get a large-scale idea of how soil health is developing over time. Erosion is a commonly known problem. In North Dakota, we also have a lot of problems with salinization. That's because rainfall has been increasing over the recent years, and that brings salts out of the earth and makes the salt concentration in the top layers of the soil a problem. And so the idea is to get an attempt to get see how that's evolving. From a technical perspective, what we're trying to do is to get more out of existing data. If you have satellite imagery with maybe 10-meter resolution, then you would need, ideally you would like to have many bands. Adding extra bands is expensive. It's not in our hands, but what is in our hands is to look at windows that can tell us about structural information. So it's about getting additional low-cost information, and I'll show a fast information-dense approach to get fractal information out of those windows. What that tells us about soil health is still a little bit vague. We're hoping that it will do that. We're currently trying to relate this to elevation data as a proxy of whether what we're seeing can be related to the salinization. I don't have results about that yet. I sort of feel a little bad to not be able to make that link back. I've had funding to do data science of agriculture for 7 years. I sort of feel myself, I wish I could make a stronger point why these techniques really are doing what they are attempting to do. I've worked with industry, large, small, researchers in extension services, with climate scientists at UND. Why is this still a little bit of a vague thing? And my view of the data science of food, energy, and water, those three really specifically, is in those areas, the answers are easy, but the questions are hard. And this is sort of playing on the Hitchhiker's Guide to the Galaxy for those who've read it, where they built this gigantic computer to answer the questions of life, universe, and everything. And the computer answered 42. So why do I say this? And these three sectors specifically have a responsibility that's more immediately tangible than most other sectors. They've got responsibility towards future generations, non-human life. In any of these areas, we know globally we're not doing great. So for the responsibility towards future generations, the most quantitative tools that address this are in my sense, are the environmental footprints. We're using, so there are footprints. There is the overall ecological footprint, and there are carbon footprints, water footprints, and several more other footprints. And how much we're overusing depends a little bit on which one of them, but we're overusing for most of them. What that means is that we know already that somewhere it has to come down. Not only that, as we're overusing, the sustainable level may itself go down. And this is, these phenomena, I mean, one of the reasons for this are time delays, everybody is familiar with overfishing, overhunting, and so on. If you take out more than you should, ultimately it will backfire. And we've got the same with the atmosphere. I mean, we know we are pumping more atmospherically active gases out than will be sustainable, so it will come down at some point. Non-human life is even more complex topic. And you may think, well, we all write grant proposals with nice broader impacts, right? I mean, so it certainly can't affect us. But the problem is that there is no science of what are the right problem statements, and my current grant, sort of the overarching goal is how does a changing climate affect agriculture in North Dakota? Well, if we did this naively, and we don't do it naively, of course, but if we did do this naively, we know already the outcome because climate has been, temperatures have been warming dramatically over the past 10 years or so, and farmers have responded to this, and they have responded by planting corn and soybeans instead of the traditional wheat and edible beans, so pinto beans and these kinds of beans. Their feed crops, and the feed crops have higher footprints, so in almost any measure. They have lower calories per acre and so on. So this is may actually, if we did ask how agriculture affects climate, that may not be the wisest choice. But of course, if we had written this into our grant, we couldn't. In North Dakota, we probably would not have found people in the agriculture sector who would be willing to work with us, because nobody likes to be asked whether they're making matters worse. Our community doesn't like to question whether we might make matters worse, but I see this as a really fascinating ethics problem that's not usually discussed as ethics. I've published 3 papers meanwhile on this matter, so if you have more questions about this, I can talk about that, but that's not the main focus of this talk. The focus is on the large-scale mapping of soil health. So how does this relate? Well, if we want to get information about these environmentally sensitive topics, it gets a lot harder to get data, because you can't sort of, I mean, farmers would like you to build trust, which is essentially that you don't ask the unpleasant and uncomfortable questions. With UAS data, I mean, initially it seemed it would be free, but then more and more concerns are coming up. I've personally experienced the situation that I had access to data, and then suddenly I didn't have access to data anymore because the interests of the company had changed, and that's just something that at some point I decided, no, I'll just work with public data and try to science the most out of it. So that's really the background. How we can do the most science with the publicly available data. And one natural thing to look at are fractal dimensions. The concept of fractal dimensions has been known for 50 years. The idea is some regular and some irregular structures have this property that if you zoom in, it still looks basically the way it looked before you zoomed in, just at a lower resolution. So it came out of the question, what's the shoreline of England? Well, it depends on the scale. And that's why you can never give a scale-independent answer. But what you can say is it has a dimension that is effectively higher than 1. And the way that we calculate this dimension is using the box counting dimension. There are other dimensions too, but this is the one that's most practical for this kind of application. You successively go to lower resolutions by looking which boxes are affected by whatever you're looking at. So here we're looking at these light green points. Anytime there is even one light green point in one of these squares, I painted the whole thing light green here. In the mathematical analysis, I'll treat these as 1, these as 0, and then the process of going from here to here is taking the maximum of the values in here. So I'll be calling it the max step. That's going from high resolution to low resolution. I'm using what I call a max step, and to find out how many of these boxes are light green, I will sum them. So that's what's going to be the sum step. I'll get back to that. And usually what you would do in order to get this fractal dimension is to get several different resolutions. If you have an entire picture, you might have 15 different resolutions, and you can really average over those. What we're interested in is a window-based technique where you only have something like 5 data points, but the idea is the same. As I said, there's been work on this for 50 years, but in none of the existing approaches, the focus is quite what it is for agriculture. For agriculture, we need both a justifiable measure over a limited space. So we need the local information, but we need it over a well-defined range. For any of the other applications, you can either have some large window for texture analysis or urban growth or so, where you have large regions, or you're interested in very local measures like in image processing, segmentation. You just need something that's very local, but we need both, and the only way that was possible was through this hierarchical aggregation approach, which is a little bit like a fast Fourier transform. So in every pass, we just add 4 numbers. So in the first pass, we add these 4 numbers. The next pass, we add these 4 numbers. These 4 numbers, each of which were already aggregates. In the next pass, we add these 4 numbers, and so on. And by that, we never need to do more than add 4 numbers, which is very efficient. And it works for sums. It works for max, and it gets a little bit mind-boggling because at the same time you need to do this for every window, but for the individual fractal dimension calculations, you always just need a subset. But every one of those in the subset gets reused many times, and so it gets a little mind-boggling, but it ultimately it's very fast. So here you see the local analysis of the shore of Lake Sacagawea, which is a little bit similar to this initial question of the coastline of England. And you see that if you do this over 32 by 32 windows, there's some where you see that fractal structure more than others. And yeah, there's some that are wigglier than others. I'm using some color coding here where fractal dimensions that are in the middle between 0 and 1, they are red. You have little points, little prairie potholes you can see somewhere away from the lake. Most of the lake shore is between 1 and 2. And so the color coding is so that you only see those that have reasonable self-similarity, so have this fractal property. Talked about this already, that all the other applications there somehow have somehow different goals. We tested it on well-known fractal structures. So if you use this Pinsky triangle, which is often used as an example of a fractal structure, the areas that have pixels within a window size, they appear nicely green all over. But then at some point, these triangles here get larger than the window size, so that's why you still see them as little triangles. We tried it for geometric patterns to see if it all behaves the way it's expected to. And then, so how does this look for agricultural data? You can really pin out the fields where there's something interesting going on. You have these fractal dimensions. Here the red ones are between 0 and 1, and the green ones are between 1 and 2. Does it correlate with anything meaningful? Well, clearly, so one thing we can certainly see that the non-agricultural users tend to have higher fractal dimensions in these intermediate dimensions. We also did see how, if you average over those different users, you can see that the fractal dimension is in these 0 to 1 and 1 to 2 ranges is lower for most of the classic crops, and much higher for such crops as oats, alfalfa, hay, or pasture, and the highest it is for the highly developed That's probably not so useful for the agriculture applications, because you see clear differences between the different land uses. So there's something, and even while the NDVI is so the measure for the biomass, so it's a composite of red and infrared. That may be vastly different, but the fractal dimension is relatively consistent across those land uses. To preempt the question, why does water have a high NDVI for us? Well, that's because we're looking at windows, so we are capturing a little bit of the trees around the little creeks that were in that area that we were analyzing. So we're getting different information from what we would get from the base information that we were having. From a scaling perspective, if we did the default algorithm, it would be completely prohibitive, and we do get scaling that's less than linear in the window size. In the image size is unchanged by that, but in the window size, we get a really nice scaling, so we can go to basically arbitrary window size without largely. I mean, any doubling of window size is just one additional step. And here the breakdown in the different contributions to the algorithm, the sum aggregation, the length aggregation. If anybody wants to do that, there's more detail in the paper, and I'll also be happy to talk about how to do this. So, conclusion, well, if we want to, the needs in agriculture are different from the ones where people have done similar things before. And I hope I've been able to show that we've made some progress towards that. And there's still work needed to, even with this specific, what I showed, we need more systematic comparisons. We are currently relating this to elevation data. And again, I think it's really, we should ask the question of what questions really make sense, because what I've been trying to do here is to map this green line, is the baseline dropping off. But I mean, there are of course applications. I mean, yield, which is a large part of this workshop, I mean, do we know whether it pushes up or not? By default, we can't say, because we would have to find a way to put the impact of, I mean, if you increase yield by irrigating, you would need to find out what the irrigation is really doing to the footprints. If we increase yield by fertilization, got the same thing. I think one of the things that would really be extremely valuable to come out of this community is how do we actually develop measures where we can integrate ahead of time that we don't get this drop off 20 years down the road, because I mean 20 years down the road we might still even be in the field, we might still find out if people blame us. I mean this is I decided that with the yield question it's a much more interesting one than the soil one, in the sense that well, that's the one that directly relates to feeding people, but I personally concluded that goes well beyond the scope of just one researcher, and I mean that's something that more people need to figure out. Colleges of agriculture, of course. I mean, data science of food, energy, and water. I mean, at least the food has been done in colleges of agriculture for 150 years. I think we can't forget that. But I mean, they have the same problems that we have. So that's what I wanted to say.